All right, hello everyone. We are going to do section 4.3 today. And let's see. Let's start with this. Let's remember at the end of last class, we did this problem. We used the definition of the definite integral. I asked you to use the definition of the definite integral to, first of all, write this integral from 0 to 2 of 2x plus 1 dx as a limit. And we did that last time. We wrote this as the limit as n approaches 0 of the sum from I equals 1 to n of 2 times 2I over n plus 1 times 2 over n. Okay, what we did not get to was evaluating this limit. That is what I want to do now. Let's evaluate this. This was the second portion of this question. Let's evaluate that. Okay. So I'm going to start by looking at this portion here and trying to write it in a more condensed form. So let's do that. The sum from I equals 1 to n of 2 times 2I over n plus 1 times 2 over n. Well, I can obviously do some simplification. This is the sum from I equals 1 to n of 4I over n plus 1 times 2 over n. I can multiply 2 over n by what is inside the parentheses. This is a sum from I equals 1 to n of 8I over n squared plus 2 over n. Okay. And it turns out that I could actually, by my rules of summation, I can actually distribute this sum symbol over a sum of terms. That is a rule that we did not talk about, but I am allowed to do that for a finite sum at least. This is equal to the sum from I equals 1 to n of 8I over n squared plus the sum from I equals 1 to n of 2 over n. Okay. Now, one thing that might help us a little bit is, let's see. I know a little bit about the sum of squares. I know, first of all, that the sum from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6. That's something we have used before. I'll give you another one that's a little bit simpler. Turns out that the sum from I equals 1 to n of, instead of the first n squares, maybe I just want the first n integers. So 1 plus 2 plus 3 plus 4, etc. Well, I can write that in condensed form as n times n plus 1 over 2. Okay. There's one that might come in handy here. Okay. Another one that might come in handy. Let's see. Is what if I am adding the sum from I equals 1 to n of, say, some constant, 1. Well, then this term doesn't change for my terms. It just means I'm taking 1 plus 1 plus 1 plus 1 plus 1, and I'm doing that n times. So this should equal n. I'm going to make use of those two now. Okay? So let's see. If I am, let me actually undo that. I'm going to call this term here, I'm going to call this part 1 or part A perhaps. I'm going to call this part here part B, and I'm going to solve those separately. So part A is again the sum from I equals 1 to n of 8I over n squared. This is equal to, well, the 8 and the n squared have nothing to do with the I. They do not change as the I changes, so I could pull them out front. This is 8 over n squared times the sum from I equals 1 to n of I. This is one of those sums that we just talked about. I have a condensed expression for that, or a compact expression. It's 8 over n squared, that first term, times n plus 1 over 2. I don't need the sum anymore. I can reduce that. That's equal to, some terms cancel top and bottom. I have an n term that cancels. 8 divided by 2 is 4. So that leaves me with 4 times n plus 1 over n. Okay, which I'm actually going to reduce a little bit more. This is equal to 4n over n plus 4 over n, which is 4 plus 4 over n. So this is A. And we'll remember that. That's what A condenses to. Let's look at B. Remember, B is the sum from I equals 1 to n of 2 over n, which I might think of as 2 over n times 1. And I'm doing that because the 2 and the n are not affected by the index. So I'm going to write them out front. This is equal to 2 over n times the sum from I equals 1 to n of 1. I have a compact form for this part. It's one of the ones we just talked about. This is equal to 2 over n times n, which is just 2. So this is B. Now that I have simplified those, I could say that that sum from I equals 1 to n of 8I over n squared plus 2 over n, it condenses to 4 plus 4 over n, which is A, plus 2, which is B, which is equal to 6 plus 4 over n. Okay. Now, as a last step, I want to apply the limit. I'm going to bring back the limit. The limit as n approaches infinity of 6 plus 4 over n is equal to. I can distribute that limit over the sum. This is equal to the limit as n approaches infinity of 6 plus the limit as n approaches infinity of 4 over n. That second term goes to 0 as the denominator gets very, very, very large. That term approaches 0. So this is equal to 6 plus 0, or just 6. All right. So we used limits to find the exact area underneath a curve, which was a whole lot of work. Okay. I don't really want to do that process every single time that I want to find the area underneath a graph. That one was actually relatively simple as compared to a lot of them that you see. That one actually, we began with a linear function as the degree of the polynomial, or even we could have expressions that are not polynomials. As the complication grows, then that limit becomes very difficult to find. So we would prefer an easier method of finding that area. And that's what the fundamental theorem of calculus actually gives us, is an easier method of finding the area under the curve. So let's begin talking about that. And we're going to go into a bit of a theoretical discussion, more so than you're used to seeing. It is somewhat different from the one in your book, because I didn't like how your book did portions of it, but it is similar enough that you should be able to follow it. Okay, so let's start with this definition. Let's define a area function. So if I'm given this curve, let's call that curve F. And let's say I want to find the area from A to, I'm going to call this X because I want to be able to move X around. I don't want it to be a constant B. So I'm interested in this area right here. I don't have a formula for that area, so I want a way to find it. We're going to let y equals, well, let's see, I'm using x here, so maybe I should use a different variable here. Let's maybe say, let's let y equal f of t, and let's let it be a continuous function. Be continuous, and let's let it be defined. Define for t values greater than or equal to a. So this is my function f, and it's defined for values to the right of a, t values to the right of a, x being one of those. From my previous knowledge, my previous discussion of areas, I know that I can use a definite integral to represent that area. So let's let g of x be that area function. It's equal to the integral from a to x of that function f of t dt. And again, I'm using t because x is the upper bound of this function, which can move around in our cases. We want it to be able to move around, but I have to choose a different variable here. I'm going to call this my area function. It's my area function. Okay. you might observe that as x changes, so does the area in question. As I move x to the left, this area underneath here gets smaller. As I move x to the right, that area gets larger, at least for this particular graph. But I probably don't want to move x to the left of a because f of t is only defined there. So we might say that that area function is defined only for t that is greater than or equal to a. Okay? So I've got that set up. Then for a given x value, a given value that we use here, I can use this function to find that area in question. And maybe let's use a specific example, okay? Let's say that I have this graph, except I don't want to use red there. I want to use black. Let's say I have this function here, and let's put some numbers on the axes. Okay. And let's say maybe this function goes up here and down there, and then up again, and then crosses again at 5. So this is my function y equals f of t. And another piece of information, or several pieces of information that I'll tell you, is this area here is 28. This area here is 3, which of course I understand to be a -3 because it's below the x-axis, or the t-axis in this case. This area here is 30. Given that, let's define a second area function. The first area function, g of x, we will define as previously, except I'm going to use a constant value for a. Instead of just a general term for a constant, I'm going to say let's let it be the definite integral from -2 to x of f of t dt. And that's typically how the area function is defined, is I have a constant here, and it goes up to this term, which I can use a variety of numbers for. Let's see. This is defined for x greater than or equal to 2, or t. Yes, let's go for x. It's defined for x greater than or equal to -2. Okay. Something you might observe about this area function, you might observe that g of -2 is equal to the integral from -2 to -2 of f of t dt. And from what we did yesterday, if this bound matches that bound, then I'm actually finding the area of a line, which is 0. So the area has a minimum value of 0. So that's something that I could note. Let's define a second area function. Let's say, I'm going to call this second one capital F of x. And it is equal to the integral from 1 2x of f of t dt. So very similar to g of x above, except this one begins at 1. So it is defined for x greater than or equal to 1. Defined for x greater than or equal to 1. And similarly to what we did above, I can note that f of 1 is equal to the integral from 1 to 1 of f of t dt, which is still 0. So I have two functions that I'm defining, both of which give area for this particular graph. I'm going to use those two functions now. Okay. So let's do some work with those. I just wrote the functions at the top right so we have more room. Let's find the following. Let's find g of 1. That's equal to the integral from -2 to 1 of f of t dt. Oops. Of f of t dt by simply in this first function replacing x with 1 in both locations. I can find that. And I can look at my graph to see what that gives me. I'm looking for the area underneath the function f and the x-axis from x is -2 to x equals 1, or t is -2 to t equals 1, I should say. So for t is -2 to t is 1, the area underneath this, we're told, is 28. This is equal to 28. Okay. G of, say, 2 is equal to the integral from -2 to 2 of f of t dt, which is again equal to the net area from t is -2 to t is 2 underneath this function f, or between it and the x-axis. So I know that the area from -2 to 1 is 28, and then from 1 to 2 is below the x-axis, so that is 3. So this is equal to positive 28 minus 3, which is equal to 25 units.